So I want to just kind of reiterate a little bit what we did last time with the diffraction, and then I want to start going after the new stuff. The new stuff is going to be the Bohr atom, and I'm going to start with kind of the basic Bohr atom that's normally done, and then I want to show you how you can make it a lot more special if you do something to it. And so that'll be probably on Friday. I'll show you how to generalize this, and you're going to find out that the Bohr atom can do a lot of things. Okay, so that's it. Let's just do a quick review of X-ray diffraction. Okay, so what do? We have basically our target here. So here's our target. We send our X-rays in here like this. This is our incident beam. Okay, and what do they do?
They refract at some angle alpha.
They're going to scatter here like this, and this is your detector. And so what are you going to take with that detector? You're going to move all the way along here like this. You're going to move this. And we call this angle here. This is always your alpha. This is your slope. So this is a measure. And the detector measures your intensity. Now, if this is monochromatic, give me two ways you can think of the intensity.
Just number of photons.
Just the number of photons per unit time per unit area coming in. Or just your photon number. In general, normal, when most people say intensity, they always put energy in there as well. But I think what Scott Mister does is set up here is I think it just does count photon number. But in general, it's actually the intensity is going to be your energy per unit time per unit. So this is measured as well. So if we blow this up, what do we have here? So we have this little crystal here like this. Here's a little crystal. We said we could have the beam coming in here like that. And if this crystal wasn't here, that would normally go in like that. That would continue to be here. That's if this crystal wasn't here, but then this reflects like this. So where's our alpha here? And this right here is alpha. And we could also have then beams coming in like this and going out like that. And what do we want these two beams to do?
Interfere constructively.
We want them to interfere constructively. And then this distance here, what do we call? This is your
D.
This is your D. And that D is going to depend on we give it some subscripts. What are they?
Miller indices HKL.
Yeah, this is going to be your HKL here like this. And they're going to be the Miller indices for these planes here. So what this is some Miller index plane here, some Miller index plane here like this. That D is always what? It's the separation distance between your Miller planes. But I want another word for separation. It is the perpendicular distance here. That's what you get together. And what did we do? We looked at this little distance here. And I could drop a perpendicular here. I could drop a perpendicular here like that. And then we said that this ray here travels this distance and goes like this. This ray travels that same distance here. And then that same distance here. So this part here and here, this is your path difference. What did we say that path difference is?
Is that the 2D sign equivalent?
Yeah, where's our theta?
The top.
Yeah, we have the theta here. This is your theta here. Okay. So that's your theta like that. And so this path difference here is your 2D sine of theta. And if we want 1 and 2 to interfere constructively, we want that path difference to be?
Integers of the wavelength.
Yes, we want this to be n lambda for constructive interference. Why don't we worry about destructive interference?
You wouldn't
measure anything. Oh, we put the detector here, we didn't measure anything. Yeah. Okay, that doesn't really help us any. But that's you want to measure something there. Okay. And so our main equation is going to be this. It's going to be this 2D sine of theta equals n1. What do we call that?
Bragg's law.
Bragg's law. And again, it's a father-son team that did that. Okay, and these ideas are so used today. So if you take, when you take Scott Mister's X-ray diffraction class, just as X-ray spectroscopy, you're going to be using that law. That's going to be basically your worksheet here. So what do you get then from you measure this? When you measure this? You measure basically your alpha here, because that's coming in. That'll give you the theta. You know your wavelength. So what is this giving you? D. It's giving you the D here from this. Okay, it's giving you the D. That makes sense. Why is that important? Because if you measure the D, you can start then determining what the structure of these materials look like. And this can get really complicated, actually, quite well. Scott Mister has a graduate student, Jess. I think her name is Jess. Before she started working with Professor Mister, she did a lot of stuff with, there's a company that basically, they're basically given crap. And you don't know what's in the crap. You have to figure it out. And so what do you have to do? You basically have to do X-ray, but there's 20 components of this stuff. And, you know, it's all often very highly toxic. And what you have to do, what you have to do is that it's really, really sophisticated. So this can get really, really complicated. Quick, definitely. That makes sense? Everyone happy with that? All good? Okay. Yeah. So that said, and again, how can we relate D to the Miller indices?
1 over D squared is equal to.
So what do we know? We know that this guy here is
H squared over A squared.
that's only for one crystal. So 2 pi over
Oh,
magnitude of G. What is your G? It's always perpendicular to the continuum, and this equals what? How's it related to the
HB1.
This is your HB1 plus KB2. This LB3. And what are your B's? The reciprocal lattice. They're related to the A vectors, which are actually going to be basically the vectors you're going to use to construct your lattice. Are they connected again?
E1.
2 pi
A2 class
A2 cross A3
over
all over
J1 dot.
the volume of that parallel pipette. You take the magnitude here of this A1 out this A2 cross A3. Yeah. Then you cyclically commute the top ones, get the other ones. Okay, that makes sense. Okay, questions for that? So that what we've done here, this is a really, really sophisticated calculation. Again, this is never done in general. This is never, you will not find any book that actually does this in modern physics. Okay. Questions? Okay, let's go on historically a little bit, and then we'll tie this into. I want to show you a little bit more about X-rays, but now we want to get the Bohr atom, and then once you get the Bohr atom, I can tie this back into X-rays again. Okay, so before we look at the Bohr atom, some history. So two things that are historically important is historically the atom was first viewed with Thomson's, J.J. Thomson's plum pudding model. And it is actually called a plum pudding. They already at this point here, just the fact that people had atoms, this was already revolutionary. Historically, what's kind of interesting here is that at some point during the late 1800s, it became obvious that atoms existed, where they thought it was obvious. And there's a fellow by the name of Boltzmann who actually then figured out, he took atoms seriously and he figured out basically the statistics on all of them. It's called statistical mechanics. He's the father of statistical mechanics. Very, very famous physicist. Unfortunately, he got hold of somebody did an experiment. This experiment indicated that atoms do not exist. And so he realized he wasted his entire life basically studying these systems that don't exist. And then he killed himself because he realized he wasted his entire life. Well, guess what? The experiment was wrong. Okay, atoms exist. Never take your science to that point where you're gonna kill yourself. That's just nonsense. But that's what happened. So already the fact that they had atoms here, that was already novel enough. Now, what is the plum pudding model?
Isn't that just where the like parts of the atoms were spread out?
Yeah. So basically, people knew that electrons existed and protons existed, and they're the atom. So the question is, where is it? Where are the electrons? Where are the protons? He basically made a plum pudding model out of it. He put them everywhere. So in the plum pudding model, here you basically had positive and negative charges on one. Okay, so this is the J.J. Thomson plum pudding model. That's a great model. It can be tested. And who tested it? I don't know. Rutherford. Okay, so Rutherford tested plum pudding. Okay. How did he test it? Yeah, so radiation had been discovered, and one of the types of radiation is called an alpha particle. What is an alpha particle? It's a helium nucleus. So what he did, he took alpha particles here. So here are alpha. Alpha particles are basically helium nucleus. Okay, so it's these. And he fired on that gold foil. So this is actually gold foil. Am I still on the board? If I am on the board, let's check something. That's all looks happy. And basically the alpha particles scatter. And he measured this thing called alpha with detector here with gas. And what he did is he made an assumption here. There are two cases in physics, actually in history, where fundamentally people made really bad assumptions. And it turned out the bad assumption they assumed actually worked. We could actually get the correct answer. And this is one of them. So Rutherford realized in his data implied all the positive charge was located at the center of the atom. Okay, and he did this using classical mechanics. Okay, you fundamentally can't use classical mechanics to do this calculation. However, if you do, it gives you the right answer. Okay, so I find that just amazing here. So even though using, I'll just call this CM here, classical mechanics is fundamentally wrong. He didn't set it down. It gives the correct answer.
What about classical mechanics is wrong in that situation?
I'll show you the picture that he had there. That's, he would have had no hope of doing the quantum mechanically yet, because it didn't exist yet. It gives the correct answer. So in his view, Rutherford's he had this set. Here's the nucleus. And here's your alpha particle, which has a positive charge here like this. So what's going to happen here? Well, this is positive. The data showed that. So this is just going to come in here and go like that. It turns out that this actually, when you do this, you actually use classical orbit to do this. The calculation is quite beautiful. So you use a classical orbit here, you get this, you go through the calculation, and you get the right answer. Okay. This does not happen at all. Okay. What actually happens is a quantum mechanical process, which is a lot more complex. Okay. So you can't do that, but it gives a correct answer. That's important because it put the nucleus exactly where it should be inside. Okay. So that's where we're going to start off here. So this is still Rutherford, and this is a major breakthrough in physics, even though it's based on fundamentally law physics. Okay, so Bohr uses Rutherford's resolve to construct Zao. Okay. So I want to talk about the Bohr atom. Okay, so the Bohr atom, okay, only applies to to one particle. What's one particle? You know, I'm going to generalize this orbiting. So in this case, it's going to be a positive particle and a negative particle. So in this case, the electron orbiting the nucleus. So what we have here is this. Here's your nucleus. Okay, what do we use for the, so all the protons are in the nucleus. What do we use to designate the number of protons in the nucleus? What letter? Rawhide chemistry? Z. Right, the atomic number. So Z, this is your number of protons in the nucleus. Right, Z is your atomic number. Okay, so here's your positive thing here. Okay, and then we have one electron. So if you try to put two electrons in the Bohr model, it's not going to work. You can only have one thing orbiting. And so what he's going to do is he's just going to assume that this is a circular orbital. So Bohr assumes the circular orbit for the electron. Okay. So we're going to call this right here. This is right here. Okay. What's the problem with that? We shouldn't. So this is going to be your Bohr.
Circular orbits have an acceleration which would emit radiation, which would cause it to lose energy and crash into the center.
Exactly. So remember what happens is that we said that whenever you have a charge, and the charge has an acceleration, any accelerated charge emits EM radiation. So. Cool. From physics. 126, and we also mentioned this in this class here as well. That any accelerated electric charge emits EM radiation. So what does that mean? That means that here's your little nucleus, your little electron. This has the electron has a centripetal acceleration and will emit gamma radiation. Okay, so this is going to emit gamma radiation. So what's going to happen? That's going to leave energy and spiral in like that. So the atom can't exist. Okay. So how did Bohr solve this? And again, you can only do this is the remember I said there are two things which historically were garbage that gives the correct answer. One was the Bohr scattering experiment. This is the other one. He's going to make an assumption, garbage, utter garbage, but it gives the correct answer.
Just that it's not emitting radiation.
That's what he did. He says, well, you know, obviously atoms exist. And so he says there has to be some special orbit where this doesn't happen. And he's going to give the condition for it. And he just gave it. Now, what he did is they had the result of the spectrum. And he realized he kind of back calculated what the answer had to be. And Pauli called him on it. He says, look, this is garbage. He says, you just assumed the answer wasn't in that case. He was right. But you can only do this when your nail's full. And he basically said, well, this is the way it has to be. Now, it gives the right answer, which is historically important because then a lot of quantum mechanics didn't know it properly. But it's garbage. Okay, it's just, you know. But as far as I can tell, historically, they're the only two big areas where fundamentally wrong reasoning was used to get the correct answer. Now again, they didn't realize it. Okay, so Bohr argued that there must exist some special orbits where the electron does not emit EM radiation. So these orbits are stable. And so we need a condition for this. I give you what it is. And he didn't have an argument for other than that he gave the right answer. And then Grobel is going to come along and then realize he's going to put on a better theoretical foundation. Okay. So Bohr argued that the stable orbits have an angular momentum L given by, I don't know what it is that one's an obvious one, so studied it. N, where N's an integer, H bar. And then you pronounce this H bar. The H bar is where all the physicists hang out after working very hard on Friday night. You go to the H bar. Okay, so So H bar is by definition. Anyone else defined to be? Planck's constant over 2 pi. So that's just what it is. So he stated that any electron that has basically an angular momentum given by NH bar, this N here, N is a positive integer, 1, 2, 3, the positive integer, will have a stable. Okay. Okay. Now, he just clapped his hand and made that assumption and it worked. Let me give you a little bit of a background. So de Broglie, I don't know if it was de Broglie, but helps. But just so you know, the de Broglie hypothesis puts Bohr's assumption on a better theoretical foundation. Okay, so let me give you the Broglie's argument. And first of all, on Friday we had the de Broglie wavelength. What was it? What was the de Broglie hypothesis?
If photons have a wavelength
Yeah, so
and
if
momentum,
so recall,
the particle would have.
if photons have a momentum, have a linear momentum P given by what was this? P equals
H over lambda.
H over lambda, then particles have a wavelength. Have a lambda given by HP. Okay, so let me show you how this kind of works. But here's a better argument for why this would be the case. So the circle, radius r. We have the electron moving around here. So what would the electron have? A wavelength. So what I can do is if I draw my wavelength for the electron, I can go like this. I could have something like this. What's that eventually going to do? It looks like you're going to get constructive and destructive interference, and that's not going to be stable. Right? So in this case here, lambda has constructive and destructive phases. So this is not stable. So this orbit is not stable. Okay. This is all garbage, I'm telling you. This is it's going to get the right answer. We'll eventually do this correctly. Just, okay, the hydrogen atom and all this stuff is understood well. There's always somebody who tries to challenge it. There's a student from Alfred who came by my office with his whole theory about why the atom was wrong and all this other stuff. It really didn't help his argument when he pulled up his laptop. There's a giant picture of a marijuana leaf on it. Turns out that did not believe his argument very much. It just didn't. Why? Okay, just now, what would we have happen? We don't have to have that happen. Instead, we could have this. I could have that. What's this condition here? How many wavelengths do I have here? Remember, this is a wavelength. What do we have? One wavelength, two wavelengths, three wavelengths, four wavelengths, 5 wavelengths. Okay. So what's the distance around here? 2 pi r. This is r. And this is going to be five wavelengths. Okay, generalize it. So we're going to say the stable orbits, the distance around here equals an integer n times the number of wavelengths. These will be the stable orbits. Okay, so We have that. Now, let me convince you that we can get to the Bohr condition here. So we have this right here. I can take the 2 pi over here and the land over here. Okay, we do one thing and we're basically done. What do I do to that equation? Multiply by h bar. I mean by h. Okay, what is this called?
H bar.
This is h bar. And this part looks good. Okay. Hey, does this have a name here?
P.
That's our p. So this is r times p. Hey, you've all had 125. Physics 125. What is linear momentum given by for a quark particle?
RP.
It's r cross p. So recall. The angular momentum L for a quark particle is L equals r cross p. So what do we have here? There's our p. There's our r. If this is a circular orbit, what angle does r make with p?
90 degrees.
90 degrees. So if I look at the magnitude of this is what? Magnitude of r, magnitude of p times
Sine 90 or 1.
sine of 90, which is 1. So this is what? L equals R P. So what is this? This is L. So L equals N H. Now Bohr didn't use that argument. I went to one talk where somebody gave the actual historical argument Bohr gave. It's garbage. I mean, it's really, really bad. You can only do that if you Niels Bohr. And then people will just sit there and just nod their head yes. Actually, that was a problem. So at some point, I mentioned that Niels Bohr's son Aga, who was also a very talented theoretical physicist, and they had a hard time getting honest feedback from people because they're Niels and Aga, and so no one was going to criticize. So everyone just said, yes, that has to be right. And then they came across Richard Feynman, who will study him in a little bit, who's a very well-known physicist. And he would actually criticize their work. And they really liked that because he would say, well, yeah, look, if we can go to Feynman and we're going to get an honest evaluation for the work because he doesn't care who we are, because he's going to evaluate our work, honestly. And they really appreciate it. Okay, so let's use this and actually get our hydrogen. Again, the reasoning we're going to use garbage is all garbage. Okay, but it's going to give the correct answer. One of the 3 things that predicts would be correct. The most important thing it predicts is correct. The other one's garbage. Okay. So, derivation of the Bohr. Okay, so here we are. Here's my little electron. Here's some velocity v. And here's our little nucleus here, which is going to be z. Okay. How would I set this up from general physics? If I gave you this problem in general physics, you'd say easy peasy. What would you do with this? What 2 things would come to your mind if you were to say, work on this?
Find the acceleration.
Okay, well, it's going in a circle, so we call that
Centrifugal.
circular motion. Why do we call it circular motion? It's going in a circle. Okay, so how do we do any circular motion problem? What do we always start off with this? Free body diagram. Okay. Hi, electron. Okay, what are all the forces acting on from the electron?
Force of attraction to the nucleus.
Yes, this force right here. This is your electric force. And what is that given by? For those of you who had me on 126.
Q.
K Q1 Q2 over R squared. So this is going to be your K Q1 Q2 over R squared. Here's K. Q1 is the charge of an electron minus E. What's the charge of a nucleus? And throw our Z protons in it.
Plus.
So ZE. Okay. Over R squared. And this is your force of the electron. When you do a circular motion problem, okay, whenever you have a two-body diagram, you need a coordinate system. What is the coordinate system we always have for circular motion?
Towards the inside of the radius is positive.
Yes, so we have a radial component and then a perpendicular component. So our coordinate system is going to be this radial part here. And then perpendicular. What's our sign convention? For circular motion, anything going toward the center is positive. So the sign convention is anything going toward the center is positive. So when we do this stuff net equals MA, I can write this as the net force in the radial direction equals MA radial. Net in the perpendicular direction equals MA perpendicular. This we can ignore because there are no perpendicular forces. Now, the net force in the radial direction from our free body diagram is what? This right here. But do I put a minus sign in there? No, because toward the center of the circle is always positive. So this right here has to be. K. I'll put up the Z. So I'll put the Z out here. Z Ke squared over R squared equals MA radial. What is your radial acceleration?
V squared over R.
V squared over R. So this is M V squared over R. And it cancels out with the R's, and so this gives me Z Ke squared over R. I'll take over the M as well. V squared. Does that make sense? What else would you know about this problem from first semester physics? What would be the energy of the electron? Okay, what is energy always made up of?
MB squared.
Kinetic
How much attention?
and potential. Okay, so your energy is going to be your kinetic plus your potential. But you're going to get brand new. Did I tell you what these are? What they become? Okay. You're all grown up now. Okay, you're no longer. Remember when you were a wee little freshman? You had on your little beanie, your little propeller beanie like this, and you had your little sock monkey, had your little fudgesicle like this, and you go back to your dorm and watch Scooby-Doo reruns. And you're a wee little freshman. You're all grown up. Okay, you have to put away your beanie. You might still have your little sock monkey that you slide under the pillow and no one sees it and pull it out for a little hug. And might enjoy a periodic fudgesicle and reruns of Scooby-Doo and then you're all grown up. Kinetic energy is no longer Ke, it's always capital T. For the rest of your life, capital T is kinetic energy. Potential energy is no longer U. It is always capital V. Okay. You're all grown up. Okay. Okay, what is the kinetic energy of the electron? 1/2 mv squared. What is the potential energy for two point charges? Okay. Q1 Q2 over R. What do we get now? 1/2 m v squared Now we're gonna get this right here is our minus E, and this right here is our plus ZE. So we get the minus sign, so minus K Z E squared over R. Okay, do we know anything about our buddy V squared?
The ZK.
Yes. Boom, right there. We have M Z K E squared over MR minus K Z E squared over R. Masses go out. We would not leave our answer like this, what would we do?
Now compacting.
What?
Did you drop a K in the?
Yes.
Oh, yeah, there's a K here.
Oh,
Sorry. Now what would you do? Okay.
Subtractive.
Yeah, you just get a common denominator. Well, put the top and bottom here by 2. So this gives you minus K Z E squared. What does the minus sign here mean? What does it mean to have a negative energy? What can the kinetic energy never be?
Never be
It can never be negative. Where's the minus sign coming from?
the potential.
It's coming from the potential. So what does that mean about this term here? And this term here?
That the potential is greater than the kinetic.
Yeah, but if you look at kind of the magnitude of this, the potential energy is putting out with the kinetic. So the negative sign here means that the electron is bound to the system. So the negative energy. The negative E means the electron is bound. There it is. So let's put down the 3 equations we have. So we have 3 equations. We have our energy equals minus K Z E squared over R. We have this fellow here, V squared equals Z K E squared over MR. We have Bohr's condition. L equals NH. These are the 3 equations.
There be a 2 with the arms and for energy.
Thank you. Keep me honest. We get new physics. That's just sad, Susan. Okay, so that's good to know. Okay. Imagine all the things. Imagine what we'd be doing if we actually learned physics in this course. So what can we do with this? Let's actually think over this a little bit more. So we know that L is what? This is our R times P. Does P have a name?
H over.
M times V.
Ah.
I'm going to square this. Then I'm going to take my buddy V here. Bam. Right down there. So what does that give me? That gives me R squared, M squared, MZ, K, E squared, MR equals N squared, squared. And one of the R's go out, one of the M's go out. So I'm going to take everything over here. So this gives me R, M, Z, K, E squared equals N squared, H squared. Well, my buddy R is H bar squared over Z M K E squared N squared. What's odd about this answer? What's this R dependent upon? A whole bunch of constants and an integer. Okay, so basically we're getting your R here depends on a whole bunch of constants in terms of energy here. And these are the stable orbitals. So remember your N can be 1, 2, 3, 4, 5, something like that. Now what can I do with this R now? I can take this R and put it into here, into that R. And so what does that give me? That gives me E, which is this guy, over 2. Now my buddy R is here. So what does that give me? I get minus. How many factors of K? And where are they? And where are they? On the top. Minus K squared. How many factors of E? Where are they? One of those, we have 4, E to the 4. How many factors of Z? On the top. How many factors of M? 1 on the top. What goes in the bottom?
2
So I did 2 H bar squared. Then we get our here, and then we get the N squared here with this. I can rewrite this as minus K squared E to the 4th M. Actually, I'm gonna put M first. Don't worry about why I'm putting it first. This is gonna help us out a little bit. Yeah, what's odd about that result? The energy depends on a whole bunch of constants and N. And the N is
An integer.
integer in the bottom. And these are going to be the stable energies here. So what we have here now, let's construct what the picture is. So first of all, let's rename a couple things here without doing any work. What have to be the units for this?
Meters.
It has to be a length, right? This has to be a length. Why does it have to be a length? Yeah, because basically R is a length here, N is a integer, no units. So this has to be a length here. We're going to define this whole thing here. We're going to call this A naught. And this is going to be called the Bohr radius. Okay, and you're going to work this out in daily homework that I haven't written up yet. You're going to find out that this A naught is about 0.5 angstroms. Okay, what's an angstrom? 10 to the minus 10. Okay. So what this is here is that this R, and I'm going to put an N here. So this is the radius of the nth orbital. It's going to be this A naught N squared. Okay. And all this stuff over here, this E, and I'm going to put an N here like this. So this is going to be the energy of the nth orbital. It's going to equal this minus M K squared E to the 4th over 2 H bar squared here. Z squared over N squared. Without doing any work, what do you know about that guy right there? It has to have units of what are the units for the number of protons? Integer, so it has no units. What are the units for an integer? It has no units. So this has to have units of energy. This has units of it. You're going to work out this one here too. That constant here is going to be 13.6 electron volts. So what we're going to end up with is that the energy level is the same, which is minus 13.6 EV Z squared over N squared. There's the energy orbits for those are going to be the stable ones, this A naught is squared. And the angular momentum from those, I'll just do an here like that. And then use this right here. So let's draw what this is going to look like. We're going to do two pictures here. So this is going to be the Bohr atom. This answer is correct. This is completely correct. When you actually do this quantum mechanically with the Schrödinger equation, you get the exact same result. So historically, that's what these are garbage. But we don't know that yet. We're going to draw a little picture. So our picture is going to be what? I'm going to plot the energy this way. So this is going to be called an energy level diagram. Get used to this. We're going to see these a lot. And then over here, I'll draw my little nucleus like this. So the first level is going to have n equals 1. Okay, so what would be the radius for this? Would be my R1 value according to this little prescription here?
A naught.
Yeah, this is just going to be A naught. A naught times 1 squared. This A naught. Okay, so that Bohr radius is going to give us what? It's going to give us the size of an atom. Okay, we're going to let Z equal 1. What? Okay. There should have been this is actually divided by Z. I think I dropped that factor in Z. If you work it out. I think I dropped that factor. This should be divided by Z. I think I dropped that, but Z is going to be 1. So what's the size of a hydrogen atom? The size is on the order of an angstrom. Why? Because basically this is on the order of like 0.5. So that's why your hydrogen atom has a size of 4 angstrom. Okay. 4. Now, what does this mean over here? If I look at this energy here, the n equals 1. The energy level for that is going to be, according to that prescription,
Minus 13.6 eV.
minus 13.6. Okay, now let's do n equals 2. So if n equals 2, what happens to my order? It increases by a factor of 4, right? So I can't really, I made this way too big. Okay, so this is going to get really big. That is not a factor of 4. This is R2. This is my n equals 2. So this R2 is going to be A naught times 2 squared, or 4 A naught. Okay, again, that's garbage. That doesn't happen, but the Bohr atom. So what does this become? My n equals 2. What would I have here? I have minus 13.6 over 2 squared, minus 13.6 over 4. To work that out, what does that equal? Okay. 3.4. Minus 3.4 EV. What's the biggest value n can get? Oh, 0. It can never be 0. How come? First of all, that's not big.
Wouldn't have anything more big.
If we put a 0 in here, what happens?
It was
You get negative infinity, that would be some way with low energy like that. And it's always a positive n. What's the largest n can be? If it's an integer. What's the largest positive integer?
infinity.
Infinity. Okay. What happens if I put infinity in? Then the radius becomes infinite. Okay. And then this is going to go to 0. This is going to be an energy in here. What does that correspond to? That's going to be ionization. What it's going to mean is that this electron has so much energy, we've ripped it away from the atom here. That's going to be ionization. Okay, let's put another one in here. Let's put in n equals 3. So first of all, what happens to my orbit here? It increases by a factor of 9. Okay, so it'd be something way, just preposterous out there. So this would be my R3. This would be then, your A naught times 3 squared, or 9 A naught. So where would this be? Let's work it out. So I think by 13.6 divided by 9, because if you 3 squared is minus 1.5. Let me someplace here. This is n equals 3. So this is going to be my minus 1.5. And I can also have n equals 4. So this goes out to 16 now. N equals 4 is going to be basically up here. I do this. I divide it by 4 squared, which is 16. This is now minus 0.86875 eV. Yeah, what's happening to these energy levels for the hydrogen atom?
The gaps between them are getting smaller and smaller.
Yeah, they're getting crunched and crunched and crunched and crunched. Okay. Every system will have its own unique value of energy. So this is what they do for hydrogen. They're not going to do that for everything. So any system is going to have its own unique energy system. So this would be n equals 5, n equals 6, n equals 7. They get crunched together with this. Okay. Does that make sense? So this energy level diagram is actually correct. When you actually do the Schrödinger equation, the correct method to do it, you get this material. That works correctly. That's historically important, because otherwise people would really have gone down all bad rabbit holes. Okay. Now we can do some things here with this. What do we call let's say the electron is here. So if the electron is here, that's the lowest energy we can get. The lowest energy a system can have is called the ground state. So this is your lowest energy. Lowest possible energy. This is called your ground state. Okay. Well, we can take this electron and we can excite it. So it turns out we can excite this electron up to here, and we'll see how we can excite it. It's going to absorb light. We'll see later on about that. So if the electron is up here, this is the ground state. What do you call this?
It's the excited state.
It's an excited state. But it's your first one, so it's called the first excited state. And this is your first excited state. And what's going to happen here is basically we're going to have a photon coming along here. That photon is going to hit this electron here. It's going to absorb the energy and it's going to go up to here. Well, the electron, depending on the energy here, could actually go up to here. So this is called the second excited state. So this is your second excited state. You have to be careful. If you have the second excited state, what might you naively think n is? 2. And it's really 3. You just have to be careful for that. And then so on and so forth for all these levels here. That makes sense? Now, what could happen here? You have the following happen as well. So the electron can absorb a photon of the proper energy. And be excited to one of the higher n value states. And the electron get excited to here. Here doesn't exist. All right. So you have to have basically enough energy to go from here to here, from here to here, from here to here, from here to here. You basically, the photon coming in here has to have a very specific energy. So let's do a little problem here. Let's ask what? Must lambda of an incident photon B to excite an electron in the ground state to the second excited state. So another way you can actually word this is, what must be the lambda of an instant photon to excite a photon, an electron in Iowa to New York? Right, because you think about like ground states, they'd be like Iowa, Nebraska, Illinois, things like that. One be excited says like New York, California, New Jersey, you're excited. When you take this, it's going to be, pretty modern location of, excited electron in Iowa to New Jersey. And that's obviously means n equals 1 to n equals, what would be a second excited state? Three. See, I'll use all the modern notations so you know how to do these problems properly. We see them in research. Did my graduate work in Illinois? That state is microscopically flat. You see like a little speed bump going, mountain. Then I was in Illinois, in Nebraska for 3 years. And you would think it couldn't get flatter. Turns out it does. It's big sky country. Because there's a big sky. You're in the country. Big sky country. This. You need these values. So let's draw the picture of what we have happening. Your energy is this way. Here's our little electron. The little photon that's coming in here. This is n equals 1. The second excited state is n equals 3. And we're getting it kicked up to here. I don't know if you ever had the joy of getting a Midwest thunderstorm. They're absolutely terrifying. I always like thunder and lightning. Then I went to the Midwest and found out what a Midwest thunderstorm was. It's terrifying. But what the hell is that? Just is. You get caught in these things and you're just drenched immediately. It's just not you get a little wet, you're entirely drenched. You see this wall of just black coming at you, almost like there's a line and well, what is that? Well, that's the thunderstorm. And it's coming at me. And it's honestly, it looks just like a vertical line. It's just coming, oh no. Terrifying. How do we do this? You're a pros at this. What does that sound like from first semester physics?
Conservation of
Initial
energy.
fun.
Okay, so conservation of energy. So I'm going to say E initial. What is my initial energy here? The energy of the photon.
Plus the rest mass energy of the electron.
Oh.
Plus
Plus
13.6.
the energy of the electron here. So this is going to be the energy of your photon plus the energy of the electron in the ground state. And where's all that energy has to go?
To n equals 3.
Into the n equals 3 state. So what do we have? We have E gamma equals E3 minus E. Why does that equation make perfect sense?
HCl. E.
That's what we're going to do for that one. Exactly. Why does this equation make sense? Because what is this? It's just the difference between those energy levels. So you have to have enough energy to basically go between. Then this becomes our HC of lambda. What is our E3? As force erased it due to the limit of Blackbird's phase and science. Minus 0.15?
Minus 1.5. Minus 1.5.
Minus 1.5? Minus?
6.
Let's be careful here.
It's negative 13.
Minus 13.6. This gives you 13.6 minus 1.5. And this is equal to 12.1. You tell me how to finish it now. Does HC have a name?
1240.
I think that's about 1240 EV nanometers. Is this value here, this 12.1 is and measured in terms of
EV.
EV? This is over lambda. So my buddy lambda, it's 1240 EV nanometers. 12.1 EV they cancel, and I have my wavelength, all in terms of nanotubes. Does that make sense? Yeah, but there's a part B to this. If the electron in n equals 3 de-excites, it would be n equals 2 level. What is the lambda of emitted photon? Okay, so what's that picture here? That picture is here. So here's our n equals 3. That electron here is now going to go to the n equals 2 state. And that process and a photon. Question is, what is the lambda of this? Hey, what do we do? Conservation of energy. The initial equals E final. These cancel. I equals F. The word if is I squared, which is -1. So whenever you have the word if in a sentence, you can replace the word if with -1. Okay, let's try it another way. So let's go back to E initial equals E final. Okay, so what is our initial energy? E3 equals.
2 plus E gamma.
Yeah, where does that energy go here? It has to go into the electron, so it's energy, E2. Then the rest of the energy has to go into the photon. So E gamma is E3 minus E2. 3 minus 2 is E1. These cancel, so all gammas equal 1. So E3 is our buddy, what again? It says minus 1.5. Minus what is our buddy E2? Minus 3.4?
Yes.
So this is 3.4 minus 1.5. Uh-oh. Always embarrassing when I have to do math in my head. 1.9? Yeah. 1.9 EV. Okay. Now what?
So you just,
The same thing. Right? So we have our let's see lambda. Now our buddy here. HC is our 1240 EV nanometers. Lambda 1.9 EV. Lambda 1240 EV. 1.9 EV. Let's put this guy out. 76 something. Loves it all that. Okay. See, anyone recognize that wavelength? Engineers might. I lost the people who did some astro stuff. That's the wavelength of a red photon. Okay. So that's gonna be a red photon. Okay. Questions? I want to give you a couple of names of some things. We're gonna get a lot of mileage out of this. Oh, there's just okay, so Richard Feynman, the fellow I told you about. I guess his father would ask him a lot of questions. I think his father may have been an engineer or did something technical. And his father had read a book about basically atoms giving off light and stuff like that. And so I think he had just finished, either he was an undergraduate or maybe he had gone through graduate school. And his father said, so I've been reading about these atoms, how they give off light. He went, okay. He went, so from my understanding is you basically have a photon come in, and this electron kind of gets kicked up to another state. I went, yeah, that's right. Then it falls down and gives off light. I went, yeah, that's right. He went, well, when it's in the excited state there, where's the photon? And he went, it doesn't work that way. And I guess his father just kind of looked at him and looked, but we've sent you to school for all this time and you don't even know where the photon is in this state here, kind of education you have. Okay, I thought that was funny. Okay. What can we do with this? We do the following. He also Richard Fleming also worked on the Manhattan Project. I guess everyone had to be tested by a psychiatrist, make certain they were sane. And he had no patience with psychiatrists at all. So I guess you had to stick out your hands and you go like this. They say no the other way, you go like that. It doesn't so. E. Okay, so this is n equals 1. N equals 2. There's a reason I'm making these really wide. 5, 6, and then the infinity one is going to be here. This would be our n equals infinity. So this is E1, E2, E3, 6, infinity. Okay. So what we can do is we can look at all the transitions going to n equals 1. We can look at this one here, this one here, this one here, this one here. So these are all the transitions. To n equals 1. Okay. All the photons here are ultraviolet. So these are all UV photons. Okay. This right here, this is called the Lyman series. Uh-oh. Yeah. They're the Lyman series here. Then we can look at all the transitions too. N equals 2. Maybe this one, this one, this one, this one. So these are all the transitions to n equals 2. These are all visible. And these are called the Bohr. So you hear the word Bohr series all the time, and what that refers to is all the transitions of light given off going from here. These are all visible. Okay, this one is. We're going to look at the spectrum. I'll try to set it up and we'll look at it on Friday. This one we said is red. Okay, going from the 4 to this one is
Yellow.
blue green. Okay. And then these two right here, okay, back when I was younger, I could actually distinguish the two. I could actually, it was a good eye test. Going from 5 to 2 and 6 to 2, you get 2 lines that are right on top of each other. In my younger days, I could distinguish them. Sadly, I cannot anymore. Okay, they are purple. Okay. They're the ones you can actually easily see. And again, if your eyes are very good, you can actually see that they're right on top of each other, but they are distinguishable. Okay, we have those. Then we can have transitions n equals 3. This, okay. These are transitions n equals 3. These are all infrared. Okay. I think these are the Paschen ones. Lyman, Bohr, bracket, Paschen form. Lyman, Bohr. Okay. I'll look up the name here. This is either bracket or fund. I can't remember which one, but these are IR. All the rest of them are IR as well. So if you look at these ones here, these are the transitions to n equals 4. These are IR. And the transitions here to these ones here. These are also IR. The important ones here are this. And who would be really worried about these? Or you'd spend a long time measuring those? Who? This is from hydrogen. What profession uses hydrogen all the time? And it's the main thing you look at. An astronomer. Why do you spend all your time looking at hydrogen if you're an astronomer? Because what is most of your gas in the universe made up of? Hydrogen. And so when you look at things in the night sky, you know, these beautiful pictures, what color do you often see? Red. Why do you see so much red in basically these astronomy pictures? It's this. It's basically you're getting the hydrogen gas that's excited, it gets off light. It's primarily this one here. And that's why all these pictures are actually often very, very red. It's from all the hydrogen gas. Okay. We'll do more with this class. I guess it's over, isn't it? This technically is over. We will we'll pick up this next time. I want to modify this. And so what we're going to do is right now I've let that nucleus basically sit there and not move. It turns out that nucleus can move. I want to ask what happens if there's a little movement there. What's going to happen? We're going to get the exact same equations, but our mass is going to be replaced by something called mu, the reduced mass. And that's going to allow us to basically, I'll show you this cute little trick. We're going to be able to solve a wide variety of problems just by calculating what the mu is or something. And we're going to be able to apply this to a much wider variety of problems. Have a good day. The screen? You can just. You're welcome. Take care.
Dr. Lowe's, I've got what feels like a really stupid question.
Sure.
So you were drawing the images of the waves going around the atom, like with the electron,
Yep,
right?
yep.
With the traveling waves, like especially in optics, you know, we always talked about
Yep.
the wavefront moving forward.
Yep.
What happens to the rest of it? Does it end at a certain point?
This is all great.
Okay.
Okay, so none of this is crap. It's just basically how they extended the argument to kind of get that. So there's no, you just say the whole thing's a wave and you make up the third stuff.
Okay. But I mean, even just in traveling waves, do they end at some point? Or
They will peter out when you work out the wave functions for these that they're gonna basically there'll be something that's going like a particle. This will represent the particle.
okay.
So this is the level, but we don't know this yet.
Okay.
And so what's gonna happen with that, you have to interpret it. So basically it's, you don't really have it out here. Kind of. It's primarily here.
Gotcha.
And so we'll have to figure out what that is, but we don't know.
Okay. Thank
So
you.
that picture's garbage.
Okay. Okay.
Yeah.
I also I left my backpack in one of my teammates' cars. Would I be able to swing by later
Sure.
today?
Yeah.
All right. Thank you. Have a nice day.
You too.